cosmic rebel has burst into the solar system, spinning faster than the laws of what physics allows.
Well, an object that refuses to behave like anything natural, and just when we thought 3i Atlas was the strangest wanderer, the universe sent something even wilder.
Something unexpected happened when astronomers reviewed the latest space images, and it forced them to stop and look twice. New observations revealed that Atlas was not behaving like a quiet interstellar visitor, but instead releasing two distinct jets that slowly shifted and wobbled as it moved. These details came from fresh data gathered in late December, not from old ideas being recycled. Nothing in earlier models suggested motion this organized or this persistent. The behavior felt active rather than random, yet no clear explanation exists so far. If this object is performing actions we did not predict, then what exactly triggered them as it entered our view? The most unsettling moment in the story of Atlas was not something it did, but something it refused to do. On December 19th, the interstellar object passed relatively close to Earth at a distance of about 270 million kilometers, a range that allowed astronomers to observe it with rare clarity. For weeks, public attention grew, online discussions exploded, and quiet fears followed a simple question. What would happen when it reached its closest point? Nothing happened. Atlas did not slow down, change direction, or show any visible response to Earth's gravity or presence. There were no sudden flashes, no increase in activity, and no sign that the planet beneath it mattered at all. In a time when space stories often expect drama, this silence felt strange. Objects entering planetary neighborhoods usually react in some way, even slightly, yet this one continued on its path as if Earth was not there. This lack of reaction matters because it removes one of the most common explanations people reach for. If the object were unstable, damaged, or strongly influenced by nearby bodies, this was the moment we should have seen it. Instead, Atlas stayed consistent, holding its course and behavior steady. That calm movement made scientists pause, not because it was dangerous, but because it was controlled. The contrast was hard to ignore. On one side, there was growing anxiety among observers and social media voices fueled by dramatic headlines and imagination. On the other, there was a cosmic visitor that behaved with complete indifference. It neither approached nor avoided Earth. It simply passed by, silent and focused, as if its journey had nothing to do with us. This raised a deeper question about intent and direction. Even without assuming intelligence, if Earth did not matter, then what did? Astronomers began to shift their attention away from our planet and back toward the object's broader path through the solar system. Its trajectory suggested purpose in motion, not in interaction. The story was no longer about a near miss, but about a destination ahead. Distance also played a key role in shaping this moment. 168 million miles may sound large, but in cosmic terms it is a brief encounter. During that window, instruments captured clean data without interference or sudden change. That consistency allowed researchers to rule out several possibilities and narrow their focus to long-term behavior rather than short-term reactions. In space science, silence can be just as meaningful as action. The quiet pass of Atlas told observers that whatever drives this object does not respond to nearby worlds in obvious ways. It follows its own rules, its own timing, and its own route across the solar system. If Earth was only a passing landmark and not a point of interest, then where was Atlas truly heading, and why does its path seem so deliberate as it moves farther away? The defining feature of Atlas is not its shape or its brightness, but its speed, because nothing observed before has moved through the solar system quite like this. Measurements show the object entered our region of space, traveling at about 36 miles per second, then accelerated to nearly 42 miles per second at perihelion, For a general audience, that means it was moving faster than any known comet or asteroid ever recorded, crossing vast distances in the time it takes most objects to slowly bend and drift. This extreme velocity changes how gravity affects the object. When slower visitors approach the Sun, its pull has time to curve their paths, often reshaping their orbits in dramatic ways. With Atlas, that process barely happened. Even after passing close to the Sun, its trajectory shifted by only about 16 degrees, a small bend that surprised many researchers. The Sun did not capture it, slow it down, or redirect it in any meaningful way. Instead, the object continued forward with almost the same direction it had before entering the inner solar system. To understand why this matters, it helps to imagine a comparison. A slow-moving object behaves like a leaf drifting in water, easily pushed and turned by surrounding forces. Atlas behaved more like a bullet fired through space, too fast for nearby gravity to grab hold for long. This does not mean gravity stopped working, but it means the interaction window was short, precise, and limited. That alone places this object in a rare category. Speed also affects how much information scientists can gather. High velocity reduces the time available for close observation, which is why the data collected during its approach became so valuable. Every hour mattered. Instruments had to capture details quickly because the object was already racing away almost as soon as it arrived. That urgency shaped how researchers interpreted each signal, image, and measurement. There is another reason this velocity raised questions. Objects formed within a star system usually share some of its motion, shaped over millions of years by local gravity. Atlas did not behave that way. Its speed suggested it came from far beyond, carrying momentum from a different stellar environment. Whatever pushed it into interstellar space did so with tremendous force, and that energy remained intact across unimaginable distances. This realization forced scientists to rethink earlier assumptions. The object was not just passing through, it was cutting through. Its motion did not adapt to its surroundings, and its path showed little sign of negotiation with the forces around it. That consistency made the later discoveries even more striking, because any unusual behavior could not be blamed on slow chaos or random drift. Speed in this case became more than a number. It became a clue. It suggested a history shaped by violent ejection, long travel, and minimal interference. It also hinted that whatever we were seeing now had survived conditions far more extreme than our Sun could offer. If Atlas moved through the solar system like a projectile rather than a wanderer, then how could it still produce stable structures and organized activity as it raced onward? The moment scientists realized that Atlas was releasing 2 jets instead of 1, the story entered unfamiliar territory, because this behavior does not follow the patterns usually seen in comets. High-resolution images revealed streams of material pushing outward from the nucleus in different directions, both stable enough to track and active enough to change over time. This was not a brief outburst or a single flare. It was a sustained structure that demanded attention. Even more surprising was the presence of an anti-tail, a long glowing feature stretching toward the Sun rather than away from it. In most comet encounters, solar radiation and charged particles push dust and gas outward, forming tails that always point away from the Sun. With Atlas, the opposite appeared. The anti-tail extended for more than 1 million kilometers and remained visible for months, growing into a defining feature instead of fading out. This matters because temporary effects are common in space, but persistent ones are rare. A short-lived event can be explained by a sudden crack or a burst of trapped gas. A structure that lasts across weeks and months suggests balance, not chaos. Observations showed that the anti-tail did not randomly flicker or collapse. It held its shape while slowly shifting, as if guided by a consistent process rather than chance. the two jets added another layer of complexity. Instead of spraying material evenly, they appeared focused and directional. Their movement showed a gentle wobble that matched changes in orientation, which allowed scientists to connect the jets to the object's rotation. This link between motion and structure suggested organization at the source, even if the mechanism remained unclear. For a general audience, the key point is not what theory explains this behavior, but why it stands out. Space is full of debris and ice, yet most objects respond to sunlight in predictable ways. Atlas did not simply react. It maintained a configuration that resisted disruption while racing through the inner solar system. That combination of speed and stability made simple explanations harder to accept. Researchers began comparing this object to known comet models, and the differences kept growing. The anti-tail orientation, the jet persistence, and the symmetry seen over time did not match what would be expected from a fragile body breaking apart. Instead, the structure looked maintained, as if the forces shaping it were steady rather than violent. This does not mean the object is artificial, and scientists remain careful with their language. However, it does mean that familiar rules no longer offer full answers. When natural systems behave outside their usual range, they force new questions, not conclusions. The longer these features remained visible, the clearer it became that Atlas was not just passing through in silence. It was actively interacting with its environment in a way that had not been recorded before, and it was doing so without losing its form. If two stable jets and a sun-facing anti-tail can survive under such intense conditions, then what does that reveal about the internal structure and rotation of this object as it continues its journey? One of the most puzzling discoveries about Atlas is not how fast it moves or what it releases, but how it is oriented in space, because its rotation axis points almost directly toward the sun. Measurements show this alignment falls within about 8 degrees, a range so tight that it immediately caught the attention of researchers. In natural systems, rotation axes tend to point in random directions, shaped by collisions, formation history, and long exposure to uneven forces. This case looks very different. To understand why this matters, it helps to think about probability. The chance that an interstellar object would arrive with its spin axis nearly lined up with the sun purely by accident is extremely low. Scientists estimate it at well below 1%. In simple terms, this is not the kind of result that appears often when randomness is involved. It suggests either an unusual past or a process that keeps the object locked in this orientation. This alignment creates a strange physical outcome. One side of Atlas remains in constant daylight, while the opposite side stays in permanent darkness. That condition is rare for small bodies moving freely through space. Most objects tumble or rotate in ways that spread heat over time. Here, heat and energy are delivered unevenly and continuously, which can shape surface activity in unexpected ways. The effects of this setup can already be seen. Jets and emissions appear connected to the same regions, as if certain areas are repeatedly activated while others remain quiet. This steady exposure could explain why the activity looks organized rather than scattered. Instead of random bursts, the object shows patterns that repeat and hold over time. What makes this even more surprising is the object's journey. Atlas did not grow up under the sun's influence. It traveled through interstellar space for ages, exposed to weak radiation and long stretches of cold. During that time, there was no obvious force to align its rotation with our star. Yet when it arrived, the alignment was already in place. Researchers have explored several possibilities. One idea suggests that the alignment could have formed long before arrival, perhaps during a violent ejection from its original system. Another proposes that subtle forces, acting steadily over time, locked the object into this orientation as it approached the sun. Each explanation has challenges, and none fully solves the puzzle. For a general audience, the key point is not which theory wins, but why this detail stands out. Rotation is a basic property, like speed or direction. When it behaves in a way that breaks expectations, it hints at deeper structure and history. The alignment tells us that Atlas is not simply spinning at random. Something shaped it, and that shaping left a clear signature. Scientists remain careful not to jump to conclusions. Alignment alone does not prove design or control. However, it does narrow the range of explanations that still work. The object's behavior now needs models that can handle precision, persistence, and stability all at once. If the rotation axis of Atlas is locked so tightly toward the Sun, then how does that orientation influence the rhythmic changes in brightness that observers begin to notice next? One of the most striking signals from Atlas appeared not in its shape or speed, but in its light, because observers began to notice a steady rhythm that repeated every 16 hours. This was not a random flicker or a slow fade, but a clear cycle in brightness with changes close to 20%. In astronomy, patterns like this demand attention, since light often carries the clearest clues about what is happening inside a distant object. At first, some researchers suggested a simple explanation. Many objects brighten and dim as they rotate, especially if they have uneven shapes that reflect sunlight differently. A long or lopsided body can act like a spinning mirror, sending more light toward Earth at certain angles. This idea works well for asteroids and some comets, and it usually explains repeating brightness cycles. However, that explanation began to fall apart when deeper image analysis became available. Data showed that the bright core of Atlas contributed less than 1% of the total light being measured. Even if the object were spinning in the most extreme way possible, such a small source could not produce brightness swings as large as 20%. The numbers simply did not match. This forced scientists to consider another source for the rhythm. Instead of rotation alone, attention shifted to the material surrounding the object. Jets of gas and dust, already seen in earlier observations, offered a new possibility. If those jets were pulsing or strengthening on a regular schedule, they could change the total light we see without relying on shape or spin alone. To help explain this idea, researchers used a simple comparison. They described the behavior like a heartbeat, where pressure builds and releases in repeating cycles. In this case, the object itself would act as the source, pushing material outward into a glowing cloud, then easing off, only to repeat the process hours later. Each pulse would slightly thicken or thin the surrounding gas, changing how much sunlight it reflects. What makes this especially interesting is how consistent the timing appears. A 16-hour cycle suggests a stable internal process rather than a chaotic one. Random cracks or surface collapses do not usually follow such clean schedules. Consistency hints at structure, even if the nature of that structure remains unknown. For a general audience, the key takeaway is not that the object has a heart, but that its light behaves in a way that feels organized. Natural objects can be complex, yet most show messy signals shaped by chance. Here, the repetition stood out, adding another layer to an already unusual profile. Scientists remain cautious. A rhythmic signal does not prove anything on its own, and alternative explanations are still being tested. However, the heartbeat-like pattern fits with other observations that suggest stability rather than breakdown. It aligns with the steady jets, the locked orientation, and the controlled behavior seen earlier. If the brightness of Atlas rises and falls like a pulse instead of a spin, then what does that rhythm reveal about the chemistry and material being released into space? The chemical makeup of Atlas adds another layer to the mystery, because recent measurements revealed a ratio that scientists rarely see in natural space objects. Observations showed methanol appearing at levels hundreds of times higher than hydrogen cyanide, a balance that immediately stood out. In most comets, these substances appear in far closer proportions, shaped by similar formation conditions and temperature histories. This difference matters because chemistry acts like a record of the past. Methanol is not just another frozen gas. It is considered a key building block in prebiotic chemistry, meaning it plays an important role in reactions that can lead to more complex organic molecules. On early Earth, compounds like methanol helped create the chemical pathways that later supported life. Seeing it dominate so strongly in an interstellar visitor forces scientists to ask where and how this material formed. Hydrogen cyanide usually tells a different story. It is common in many cometary bodies and often linked to cold, dark environments where simple molecules freeze together over long periods. When methanol overwhelms it by such a wide margin, it suggests that the object experienced a very different chemical history. Either it formed in an unusual environment, or it was processed in ways that altered its original makeup. What makes this especially interesting is how this chemistry fits with the earlier observations. The steady jets, the organized light pulses, and the stable orientation all point toward controlled release rather than random breakdown. If the object were simply falling apart, scientists would expect a messier chemical signal. Instead, the data shows selectivity, as if certain materials are being released more efficiently than others. For a general audience, it is important to be clear about what this does and does not mean. The presence of methanol does not suggest life, intelligence, or intention. Space is full of organic compounds, and many lifeless bodies carry them. The significance lies in the pattern, not the ingredient itself. When chemistry breaks from the norm, it narrows the list of explanations that still make sense. Researchers are now focusing on how this material is escaping the object. If methanol is being released through slow sublimation of buried ice, the speed of the jets should be relatively low. If the outflow turns out to be much faster, then standard comet models struggle to explain the behavior. This is why upcoming spectral measurements are so important. Speed, temperature, and composition together can reveal whether the process is gentle or forceful. In this way, chemistry becomes more than a side detail. It connects directly to structure, motion, and energy. Each molecule detected adds another clue to the story of where Atlas came from and what shaped it along the way. If methanol dominates what we see escaping from this object, then how might those chemical choices influence its next major encounter as it moves deeper into the solar system? The next major moment in the journey of Atlas will not involve Earth or the Sun, but Jupiter, because in March 2026, the object is expected to pass near a boundary where gravity quietly changes the rules. Calculations show that Atlas will approach Jupiter at a distance close to 33 million miles, a region known as the Hill radius. This is the zone where Jupiter's gravity begins to dominate over the pull of the Sun. For a general audience, the Hill radius can be understood as a line of influence. Inside it, a planet becomes the main authority, shaping how nearby objects move. Outside it, the Sun still leads. What makes this encounter unusual is how precisely the projected distance matches that boundary. It is not a deep dive toward the planet, nor a wide miss. It is a near-perfect skim of a gravitational edge. This matters because Hill radius regions are not just empty space. They are areas where motion can slow, shift, or briefly stabilize. In similar zones around planets, astronomers often find Lagrange points, locations where gravitational forces balance in a way that allows objects to linger with little effort. These are the same kinds of places humans use for long-term observation platforms, including where we position the James Webb Space Telescope to maintain a steady view of the cosmos. When scientists noticed that Atlas would pass through this region, it raised quiet curiosity rather than loud alarm. No one suggests the object will stop or orbit Jupiter. Its speed remains extremely high. Still, the timing and placement feel precise enough to invite questions. Even a brief interaction with a strong gravitational field can reveal hidden details about mass, structure, and internal stability. If Atlas carries unusual internal features, this encounter could expose them. A fragile body might show stress or altered motion. A compact and balanced object would pass through with little change. Either outcome provides information, and astronomers are watching closely for subtle shifts that instruments can detect. What stands out is how this moment fits into the larger pattern. First came the silent pass by Earth, then the extreme speed near the Sun. Now comes a measured approach to a gravitational threshold. Each stage feels distinct, yet connected by timing that appears almost deliberate. Even if nature alone is responsible, researchers remain careful with their language. Coincidences do exist in space, and large numbers increase the chance of striking alignments. Still, when multiple rare features line up in sequence, they deserve attention. The Hill radius pass is not proof of intent, but it is another point where expectations are tested. As Atlas moves toward Jupiter's sphere of influence, the question is no longer about where it has been, but about what this encounter might reveal before the final chapter begins. The story of Atlas is now entering its final observable phase, because scientists estimate that by spring 2026, it will fade beyond the reach of our telescopes and continue outward, not to return for thousands of years. What remains is a trail of unanswered questions shaped by speed, structure, chemistry, and timing that refuse to fit easy labels. This object did not rush toward us, and it did not react when it passed, yet every detail hinted at order instead of chaos. So what do you think we just witnessed? A rare interstellar comet, or a sign that our models are still incomplete? Share your thoughts in the comments and follow for future updates as new data arrives.